Welcome to the Algebra 2 Chapter 11 review video. Now I'm going to take a little bit of a different format with this Chapter 11 one. What I've got on this video is just the key itself, which is also on the haiku page on the class website. But I just wanted to talk through, because there's so much writing, I don't want this video to be like an hour long as you wait for me to write out everything that I'm saying, but more so it's to explain why we have written what we've written for our answers and what in the language of how the problems have been provided is leading us to write what we have. So as far as content goes, skimming through this, yes, you're just going to see the same things that are on the key that I've posted, but hopefully by talking through them, we understand the language and why we've answered in the way that we did. So let's get started. All right, the first part of our review, it's going right through the chapter. We start off just by looking at experimentation versus observational study. So there's one of our first vocab words. So candy bar researchers want to know whether more teenagers or adults buy their product. Is this research topic best investigated through an experiment or an observational study? Well, if you look at what they are asking for, it's not a cause and effect question. It's not like is a certain drug causing something to happen where we'd want to test it versus a placebo. So really what you're looking at is, if you're a candy bar researcher here, you want to look at the sales data and see what kind of correlation you can find. That's an observational study. So somebody is going to record all those candy bar sales and decide, are more adults or more teenagers buying their products? Not cause and effect, just a correlation. That's why we want an observational study in this case. All right, number two, your local movie theater is looking at adding a matinee to their weekend movie schedules. To help them make a decision on this, they want to find out how many people would attend this matinee movie. Make sure it's worth their time and effort in order to provide that. A researcher makes phone calls to random members in your town. What is the sampling method being used? Now, if I'm the teacher grading this, I could see two different possibilities happening. The first one is you can look at this as a convenience sample. Okay, so maybe they're only making phone calls to random members in your town. Well, they're just calling people that are local, so you think of that as a convenience sample, and I think you could defend that, definitely. Letter B, is this a biased or unbiased sample? Well, if we're seeing it as a convenience sample, then it would definitely be biased, right? Because if we're only surveying people in our town, then we're not including any moviegoers that may be in nearby towns. So their opinions aren't included in our survey. Okay, now let's go back and see how else we could have interpreted that. We could have said, oh, that's just a random sampling of people in the town. Maybe the town is the population that they're looking at, not a bigger area. In that case, it would just be a truly random sample. And if it were a random sample, then it would not be biased because we're including the entire population. And again, the difference between those answers is just whether we perceive that movie theater calling the population the surrounding area or just within that town. That determines those two answers, but either of those are going to be correct in my opinion. Next, your high school is holding voting for the president of your class. Excuse me, you randomly select 5 students from every homeroom class. What type of sampling method did you use? Okay, well, they're talking about every homeroom class. Those are different groups of students. So immediately, since we know that they're breaking up the population into different groups, then what we've got is either a cluster or a stratified. And since we are randomly selecting 5 students from every homeroom class, we're choosing somebody or some people from every group. That is a stratified sample. Number 4, the wait times for customers observed from 11 a.m. to 3 p.m. at your local bank are normally distributed with a mean of 4.7 minutes, standard deviation of 3 minutes. Are these parameters or statistics? Well, looking at this, 11 a.m. to 3 p.m., that is not the entire workday. Those are not all of the hours that that bank is open, so that is a statistic. Those numeric values are referring to the sampling of customers that happened in that given time interval, not the population of customers over a given day or a given week. It's just a little snapshot of time. That's a sample. That's statistics. Number 5, a researcher wants to test the effectiveness of a new vaccine used to help resist pneumonia. The following statement describes the design of the experiment. Researcher is given 8 people who will be a part of this experiment. 4 people are given the pneumonia vaccine. Other 4 assigned the placebo. After 6 months, the members of the study are re-evaluated. Identify a potential problem. Well, right away, the researcher is only given 8 people. That is a very small sample size. There's only 8 people. The results are likely to be skewed because 8 people are not likely to represent the entire population. Okay, so how could you improve this problem with the experimental design? Try and get some of my windows out of the way. Well, a larger sample size would be the easiest fix. Or if that's too risky or inconvenient, we would need to repeat the experiment or find some way to resample that data. We need to get more than 8 people participating. All right, next, this is what we covered early on in the chapter. Our normal distributions, our bell curves. So we have a normal distribution with a mean of 35, standard deviation of 3. Find the probability that a random x value is on a given interval, and that's what they're providing in the question. Okay, we're also being provided with the different breakdowns for each little slice of our normal curve, and a z-score table is provided on the back. Here, I know it's probably very difficult to read on your screen, but I put that table here just so we could refer to it. All right, before we even start looking at all those different intervals at the left, let's fill in what our mean and standard deviation values are. So our mean is 35, and then our standard deviation is 3. So if I go up, I would go to 38 for the next division, 41, and 44. Okay, standard deviation is less than our mean. We would have 32, 29, and 26. All right, well, let's look at greater than 32. So we know that our wedges in this, go ahead and label those as 34s, 13.5s, 2.35s, and the tail ends 0.15s. That's the percentage of area of that normal curve that they're occupying. So greater than 32, well, that's 0.84, because if I look at 32 right here on the x-axis and all the numbers greater, I'm summing up 34 plus 34 plus 13.5 plus 2.35 plus 0.15. Adding all of those up, I get 84%. All right, at most 32, well, here's 32, and I want that to be the most, so I want everything less, so I'm totaling up the remainder. And since we just found greater than 32, we're just taking the complement of what we just found in number 6, 16%. So different ways of calculating those percentages. Number 8, at least 37. Well, here's the first one that appears to throw a wrench in our operation, because 37 is not a number that we see on the x-axis. 37 is falling right about here, and it's not on a clean standard deviation, so we're going to have to use a z-score there. And if we calculate our z-score, we find it's 0.7. Okay, that positive 0.7, I'm going to look at positive 0.7, so I go to 0, 0.7, find out where those intersect, and I find it's 0.7580. And since I want at least 37, that's 37 onward. And this table is calculating everything to the left. So I have to do the complement, 1 minus what my z-score table is telling me, and I end up with 0.242, or 24.2%. And I'm sorry, that one box is kind of covering the rest of that answer. It just says or 24.2%. All right, number 9, between 29 and 38. So here's 29, here's 38. Between those two values, I've got 34, 34, and 13.5. If I add those up, I get 81.5%. And finally, less than 30. Oh man, here's another case where I don't have a clean standard deviation. Here's where 30 would be, and I want everything less than that value. So I'm going to have to find a z-score again. So I run through that z-score formula. It is provided up above, and I get negative 1.7. So So in the z-score table, I go to -1 and again 0.7, and where those intersect, I get 0.0446. And since it's calculating to the left of that value, that's what the z-score table puts out. So I take that as my answer, 0.0446 or 4.46%. Okay, next, a randomized comparative experiment tests whether a muscle supplement increases human muscle density in grams per milliliter. The control group has 10 people, and the treatment group, which receives the supplement, has 10 people. Tables show the results. Okay, well, I guess it's just one table. I compiled that together for you. Letter A says find the mean yields of the control group and the treatment group. And you can see our different notation for means there within this experiment, X bar. So calculating those, it's just a mean average like we've done before. Add them up and divide by how many there are. In our control, that mean is 1.103. In our treatment, it's 1.166. And since they do provide units, we should include units as well. These numbers mean something. Okay, find the experimental difference in letter B. It didn't copy over here. It should be the treatment average minus the control average. And if I carry that out, treatment minus control is positive 0.063. Not a huge difference. Letter C says to display the data in a double dot plot. So I have that over here. I'm just going to slide the window out of the way. All right, so we've taken each value from our table of values and labeled that out by plotting points on these number lines. Made sure that from the control to the treatment group, I didn't change how I labeled those lines. I want to be able to see any movement of those points to the left or to the right. That's going to help show me not only are there any outliers, but also was there a tendency for all of my treatments to be higher than all of my controls, or show a tendency. All right, so we lay that out, and I notice that the dots are very spread out. There doesn't seem to be much change, really. There's not a big shifting of dots from a concentration in one area to a concentration in another as I go from the control to the treatment. So what can I conclude from the study? Well, the supplement made no discernible difference in muscle density, it appears. So it looks like this supplement is not really having any effect based on the results of our experiment. However, you could also claim that because there were only 10 people in each group, we don't have a large enough sample size to confirm this. So that's why we say it appears. Based on this small study, we didn't see any real difference in the muscle density. All right, and lastly, in a recent survey of 3,500 randomly selected U.S. drivers, 62% said they had received at least one speeding ticket. All right, so this survey, what is the population? Well, the population is all U.S. drivers. Remember, all is a key word when we're talking about a population. And our sample was simply 3,500 U.S. drivers. And if we wanted to describe that sample, 62% of those 3,500 had received a speeding ticket at some point. Letter B, find the margin of error for the survey. Remember, that's based on the sample size, and this one has a fairly large sample size of 3,500. So if we run that through our formula, we do get 0.0169, or roughly 1.69%. Letter C says give an interval that's likely to contain the exact percent of U.S. drivers, referring to the entire population, who have received at least one speeding ticket. And then with 95% certainty, that's just, remember, that's just another way of saying likely to contain the exact value. So this 95% has no, it has no influence on our calculation. We do not need to incorporate that 95% at all. All we are doing is we're finding the interval. Okay, they say 62%. Based on that sample size, we know 1.69% is our margin of error. We are simply going to subtract that from 62 and add that to 62. That gives us the lower and upper edges of our range. All right, and lastly, letter D, you survey 50 drivers at your school. The results are shown. Which survey would you use to estimate the percent of U.S. drivers who have received at least one speeding ticket, and explain the answer? Okay, so in our survey, which is in the little pie chart over there, we found that 86%, not 62, 86 said they have received a speeding ticket. Well, do we trust our data or the 3,500? And results should be pretty obvious. The survey of 3,500 people is going to be a more trustworthy source. That larger sample size indicates that if we were to use a margin of error, it's going to be much smaller than our small 50-person sample that we conducted. Also, since we are just surveying people at our school, it's likely to not be indicative of all U.S. drivers included in the population. So a couple different ways to justify why the 3,500 randomly selected U.S. drivers is a much more trustworthy source of information there. Okay, I realize that that was kind of quick as far as going through a review, but again, I just wanted to save time by not writing out everything on this video. I hope that it's been a beneficial experience and that you understand a lot of the language that's dictating how we're answering these questions, and also some of the language that we ourselves have to incorporate in order to answer those effectively. That does it for this review.